So, good morning, all, and obviously, good evening to the participant from India side. Uh, I welcome Professor Venkata Krishna, who is very good friend of mine from old time when I was in India and when he was in Germany also for long time.
Yes.
So we planned today to celebrate World Science Day. Every year it is announced to celebrate the World Science Day, and sometime people may be thinking that why we celebrate World Science Day, because people celebrate Diwali, Holi, Christmas. So what is this new trend to celebrate science? So one day is dedicated to World Science Day, and the purpose is that because there are reasons to celebrate science and science day, because the life was not same as we see around us in the modern time in this century. If we compare our life maybe 90s or 1950 or before that, so because of technology in every sector, so much advancement of technology in every sector, the life has changed. If we see the transportation system, if we see the display technologies, if we see the energy harnessing, civil aviation, 500 people are flying in plane and people reached in space even. And see, even this was not expected, even not going very far. But when we were in college time, even I did not thought there will be time that it will be possible to talk with the people on the other side of the world on the video calling. So how the things changed, the change is done because of technology, and we understand that the technology is the child of the science which people do in the laboratories, and basic science and particularly material science, because of the so much advancement in fast electronics, display technologies. This is the result of the people's dedication who devoted their time from long time in the laboratories to do the basic science research, either in nanomaterials or maybe in quantum dots. So we should also ask the question to ourselves that is this race is over? So no, race is not over yet. Don't expect that what will happen in further 50 upcoming 50 years. So that is why we should celebrate science, because science has helped to have better communication system, better health facilities, X-ray imaging. Like we have degrees here in our university, MSc Biomedical Technology, Renewable Energy. So we discussed something about MRI and CT scan, so many things. So how these things came into the technology? Because of the science which was done by the dedicated people in laboratories. So that is why one day is dedicated to celebrate science, and every year we celebrate here by a distinguished lecture from one of the international researcher. So this time we are lucky that we were our request was accepted by Professor Venkata Krishnan, who is a professor in the Indian Institute of Technology, Mandi, which is in Himachal Pradesh in the north side of India. And so, if you, I will not say much about Professor Venkat. He is already established researcher, but I will show you some of the link here by sharing the screen. So if you want to know more about him, let me share the screen and let me show you some links. So if you go to the this web page, which is bkngroup.org, I found the web page very good, although it was earlier a different page, but they
Yeah.
modified it to the bkngroup.org, and here you can see that Professor Venkat, he did his PhD in Germany in 2006. Later, he worked for a long time in USA and in Japan also. In 2012, he joined IIT Mandi, and now he's a full professor there. He guided many PhD students. He also established one of the esteemed Advanced Material Research Center, which is fully dedicated to material science in IIT Mandi with very good facility. So he has some very much awards and recognitions, which you can just see on this page. So many awards and fellowships, and so many people he advised for PhD. He particularly work on the green chemistry, if I'm not wrong, Dr. Venkata. And
Yes, yes, green chemistry and
yeah, and
heterogeneous catalysis.
so many publications he did recently, and also maybe earlier he was in the top 2% scientist as listed by the Stanford University and the publisher Elsevier.
Currently,
So
also I am, but
yeah, yeah, means
this
yeah, yeah,
website
yeah.
has not yet been updated,
Okay, okay, thank you, thank you.
even
So,
for this year as well.
so yeah, so not speaking much, you can just explore this web page. That is why I shared it. It is bkngroup.org, and because see, science goes nowadays with the collaboration, and we are also planning to have the academic collaboration with Professor Venkata Group. And if you also wish, you can talk with him,
Sure,
and
sure.
you can just explore the web page and his research interest. If they match with you, you can talk. So coming to the stopping the sharing now, and coming to the topic. Okay, let's celebrate Science Day by this distinguished lecture by Professor Venkat Krishnan. His side is evening, 6:30 p.m. in India now, and we have morning time. We are just opening our offices. And I'm recording the lecture as well. So those who are not here, they can later share, they can later see the video, which we will be sharing soon. So welcome, Professor Venkata. You can start. Thank you.
Thank you, thank you. Yeah, thanks a lot, Dr. Dinesh Pathak, for your warm welcome and also giving me an opportunity to speak to your colleagues and students at the University of West Indies. Let me share my screen and then get started. Is my screen visible?
Yeah, it is visible on our side.
Oh, perfect, perfect. Just have to adjust this button somewhere.
So just to announce again that if some participant will have some question, so after 40 minutes, we will discuss for 10 minutes, including with the time of vote of thanks. So we can talk some on some topics and discussions, and whatever the participant wish to have, including the faculty member here or maybe at the other place. Thank you.
Great. Yeah, thanks, Dinesh. Thanks once again for giving me the opportunity. And yeah, good morning to you all, although it's a good evening here for us. Today I'll be talking about green chemistry and heterogeneous catalysis to achieve sustainable development goals. And since Dinesh already gave quite a detailed background about me, this was a very quick slide. I'm basically from India, born and brought up in a place called Coimbatore, which is in Tamil Nadu. It's in a southern state in India. Then I did my PhD from the University of Stuttgart, where I stayed for about 4 years from 2002 to 2006, followed by a postdoctoral stint at the University of Pennsylvania from 2006 to 2010. And subsequently, I worked in Japan as a research associate from 2010 to 2012. And since 2012, April onwards, for the past 11 years, 11 plus years, I'm here at IIT Mandi, working at the Indian Institute of Technology, Mandi. And for those of you who may not know where IIT Mandi is located, it's this is the map of India, and this is the state of Himachal Pradesh. And IIT Mandi is located almost at the center of the state of Himachal Pradesh in a town called Mandi, or rather a district called Mandi. And this is where our campus is located, which is very beautiful, serene region, which is having a lot of mountains and a lot of greenery around. So this is what we call as the South Campus of IIT Mandi, and this is the North Campus of IIT Mandi. We have two campuses. In fact, it's just separated by a hill, and IIT Mandi owns this hill, although not much construction is practically feasible over there. But nevertheless, it's a beautiful place we are located in. We have about 2,800 students and 200 faculty members and about 250 staff members. These are some of the buildings in the North Campus of IIT Mandi, and our research lab is situated in one of such buildings, which is shown here. First and foremost, I would like to acknowledge all the members of my research group because it's they who have done all the research work, and I'm just in front of you presenting their works. So I would like to acknowledge them. And in today's talk, I would like to present the works of five of my recently graduated PhD scholars, which includes Dr. Tripti Chabra, Dr. Priyanka Chaudhary, Dr. Hussein Chand, Dr. Ajay Kumar, and finally Dr. Ashish Kumar. So our group is actively working in the area of heterogeneous catalysis for energy and environment applications. And within this domain, we work extensively in the field of biomass conversion, organic transformation, and carbon dioxide reduction. And these three domains we work on thermocatalytically. Basically, we prepare a lot of different type of catalyst and use them for these applications. And then we also work in the domain of photocatalysis, wherein we focus on hydrogen evolution, pollutant degradation, and nitrogen fixation. So these three domains we work on the photocatalytic aspect. Now, here comes the question, what is the need for sustainable development? When we look at the conventional approach of catalysis, this use expensive metal-based catalyst, high temperature and high pressure, and also uses harmful solvents, toxic reagents, and the process is very difficult to handle. On the other hand, when we use sustainable approaches, this will include metal-free and inexpensive catalyst, mild reaction conditions wherein low temperature and atmospheric pressure can be utilized, environmentally benign solvents, and finally, we get reduced waste and less detrimental impact on the environment. So, sustainable approach is much more preferred than the conventional approach, and our group is contributing towards how we can make some of the conventional approach to be more sustainable by moving from a more environmentally harsh condition to a more benign condition. Now, in order to do that, we have self-imposed several design constraints on the design of the catalyst, wherein we want to use only earth-abundant elements, predominantly metal-free and low-cost materials as catalysts, use of non-toxic and non-polluting chemicals and processes, use of relatively low temperature for the different catalytic reaction, which is less than 200 degree centigrade, use of ambient pressure for the catalytic reaction. For this reason, we have never purchased any pressure reactor in our group. We just utilize the ambient pressure conditions for our catalytic reactions. Subsequently, we tend to adhere to almost all the green chemistry principles, which are 12 in number. So our group is extensively focused on the green chemistry principles and following them quite strictly. And then we would like to cater to the relevant UN Sustainable Development Goals. So these are the 12 green chemistry principles, which is kind of, it's from the textbook, and our group is actively involved in following all these 12 green chemistry principles. Then these are the 17 sustainable development goals which have been postulated by the United Nations. And within the 17 development goals, we would like to focus mainly on clean water and sanitation, affordable and clean energy, responsible consumption and production, climate action, and also partnership for the goals. So these are the five main aspects of the sustainable goals which we would like to focus on. Now, coming to the catalyst part of it, I would like to introduce the main material of our catalyst, which is the graphitic carbon nitride material. So, as you can see from the name itself, the graphitic carbon nitride consists of two elements, which is the carbon and nitrogen, both of which are environmentally abundant or earth abundant elements. And these elements are kind of connected to each other in a very beautiful pattern, which is called as this tris triazine type of a pattern. And this material, the graphitic carbon nitride, can be easily synthesized by the polymerization reaction, wherein we can use either cyanamide or dicyandiamide, melamine, or urea as a precursor. And also, this graphitic carbon nitride is stable both chemically as well as thermally. So, which means that it can be used as a catalyst for various different type of reactions because it's chemically inert and also it's thermally stable. Furthermore, this graphitic carbon nitride is also amenable for surface functionalization and doping, which can tune the properties of this material. So we can functionalize it with sulfonyl groups or nitrile groups or even phosphoryl groups, or you can dope it with any heteroatoms such as boron in order to tune the acidic and basic nature properties of this material. Now, in the first work, which is on biomass valorization, I would like to talk about the valorization reaction which we have done, wherein we have converted the saccharides to 5-hydroxymethyl furfural, which is the 5-HMF, using green solvents. So, in this case, we have developed a catalyst which is called as the sulfonated graphitic carbon nitride, which is prepared from this dicyandiamide precursor. From this precursor, we prepared the graphitic carbon nitride, and then subsequently we prepared this the bulk graphitic carbon nitride, and then we prepared the layered structure of nanosheets type of a graphic graphitic carbon nitrate, and then using chlorosulfonic acid treatment, we have kind of incorporated the sulfonic acid groups onto this graphitic carbon nitrate. The beauty about this sulfonated graphitic carbon nitrate is it has both Bronsted base and Bronsted acid sites. The Bronsted acid sites come from the sulfonyl group, which are used for the functionalization, and also the Bronsted base groups come from the nitrogen, which are present in the backbone of this graphitic carbon nitrate. Then we have used the different saccharides, which include the monosaccharides such as the glucose and fructose, and also the higher order saccharides like cellulose, sucrose, and starch as the starting material. And we have converted all these saccharides to a highly selective product called as the SPI-HMF, 5-hydroxymethyl And this 5-hydroxymethyl is a platform chemical. Platform chemical means when we move from saccharides to the SPI-HMF, the 5-HMF can be converted into other more useful products which have applications in pharmaceutical industry and also in the energy industry like the fuel industry and nutraceuticals. So there are multiple applications are feasible by taking the derivatives of the 5-hydroxymethyl. And we have done all the reactions under green solvents like water, ethanol, isopropyl alcohol, and dimethyl carbonate. We have explored the different green solvents for this reaction and found that water is giving the best result. And finally, the synthesized HMF was converted to other valuable products such as 2,5-bis hydroxymethylfuran, 5-chloromethylfurfural, and 5-bromomethylfurfural. Then whenever we prepare a catalyst, first and foremost, we need to know that whether our preparation is successful or not. For that, we have to do certain characterization of the material. So we have done the X-ray diffraction characterization of the normal graphitic carbon nitride and also the sulfonated graphitic carbon nitride. And from the peak positions and by comparing it with the literature values, we are quite certain that, okay, the graphitic carbon nitride material has been prepared. However, the sulfonation cannot be evidenced from the XRD pattern. For that, we need to do the functional group analysis, which has been done using the Raman spectroscopic technique and also the FTIR spectroscopic technique, the infrared radiation spectroscopic technique. So based on this, we are able to figure it out that, okay, the sulfonyl groups are also present on this material. Then we did the thermogravimetric analysis, which indicated that the graphitic carbon nitride is quite stable to up to about 550 degrees C. On the other hand, the sulfonated form of the graphitic carbon nitride is also quite stable till about 450 degrees centigrade, which is far higher than the temperature which we are doing the operations. Subsequently, we did the morphological analysis. First is the structure, which is now clear that we are whatever material we anticipated as formed. Second is the morphology. So for the morphological analysis has been done using the SEM technique and the TEM technique. The SEM technique indicated that some sort of a sheet type of a structure is being formed, which is also reconfirmed using the TEM technique eventually from the transmission electron microscopy. We also did the elemental mapping to figure out what are the locations of each of the element present in the sample. And we also did the ADAX analysis to understand the presence of the different constituent elements. Then we did a detailed XPS spectroscopic technique in order to understand what are the interactions, the electronic interactions which are happening between the different elements involved in the sample, how the nitrogen interacts with the carbon and how the carbon interacts with the sulfur and subsequently the oxygen and the different elements involved in the sample. And since this is a surface sensitive technique, we are able to also figure it out what is the percentage composition, the atomic percentage of the different elements involved on the surface. And especially since sulfur is one of the heteroatom here and it is forming the catalytic active site, so we were able to even decipher the amount of sulfur present on the surface, and which has been found to be about 3.27 atomic percentage. Then we explored this reaction wherein the starch gets converted to glucose and fructose, which eventually gets converted into the main product, which is the 5-HMF, which is a selective product which is formed in the reaction. Then we did a detailed optimization of the different conditions. First, we optimized the catalyst amount and we found 10 milligrams is the optimal catalyst amount. Then we optimized the temperature wherein we found 200 degrees C is the optimal temperature for this reaction. We optimized the time and found 5 hours is the optimal time. Then we tried the reaction using different saccharides, which includes the glucose, fructose, cellulose, sucrose, and starch. And we found glucose gave the higher yield of the product. Although all these saccharides are giving selective product, which is the 5-HMF, but the yield of the product is different for different saccharides, and glucose gave the highest yield among the different explored saccharides. Subsequently, we also tried the use of the different solvents, which includes water, ethanol, IPA, and DMC, and found water is as the best solvent or the optimal solvent for this reaction for both glucose and fructose, which are the monosaccharides, and also for the higher saccharides such as cellulose and sucrose. Subsequently, we did the recyclability of the reaction, wherein we recovered the catalyst after each cycle and then recycled them. And we found that although the HMF is forming during the reaction, but nevertheless, there are some changes in the yield. And these yield changes are due to a compound called as humins, which are formed during the process. And these humins kind of block the catalytic active sites during the reaction. That leads to the decrease in the yield. We are able to kind of figure out what is the reason for this decrease. Subsequently, we also studied the recyclability, the postmortem analysis, wherein we found what is the structural integrity of the catalyst after the reactions, and we found that the catalyst retains its structure after multiple cycles. Then we evaluated the different green matrix parameters, which includes the environment factor, mass intensity, process mass intensity, solvent intensity, atom economy, reaction mass efficiency, mass productivity, and carbon economy. And we got very good values for each of these parameters for the different reactants, which includes the glucose, fructose, cellulose, and sucrose. All this indicates that our catalyst is green in nature. Then the obtained HMF was converted into other useful products such as 2,5-bis hydroxymethylfuran, 5-chloromethylfurfural, and 5-bromomethylfurfural in decentals using the normal process, which indicates that the 5-HMF, which is formed using our catalytic reaction, can be further converted into much more useful products by some other methods. This work was published in the journal Green Chemistry in 2019 with my former PhD scholar, Dr. Trapti Chavda, as the first author. As a follow-up of this work, we thought that if the acidic nature, incorporating Bronsted acidic nature and Bronsted basic nature on the catalyst improves its catalytic properties, why not we further introduce another Lewis acidic nature? So there is a double acid nature, Lewis acidic nature and a Bronsted acidic nature on the same catalyst, and whether the reaction yield and the conditions will improve. However, although we anticipated that the work Lewis acidic nature and the bronchodilastic nature will act synergistically, but in reality, we found that they are acting antagonistically with each other. So, in this work, what we have done is we have taken this graphitic carbonitrate, we doped the certain region elements of the graphitic carbonitrate using boron, which is a heteroatom, which induces the Lewis acidic nature to the catalyst. And subsequently, we functionalized this boron doped graphitic carbonitrate using the sulfonic acid groups. When we functionalize this groups, it kind of indicates that it has both these acidic properties. One is the Lewis acidic nature, which is brought about by the boron doping, and the sulfonyl functionalization, which is brought about by, which brings the Bronsted acidic nature onto this catalyst. So the single catalyst is having both these acidic natures, but however, they didn't work synergistically. But nevertheless, we were able to decipher why it is not working and eventually got this work published in Carbon in 2021. In yet another work, we have taken hydrochar. We have taken the hydrochar from the waste orange peels, and then we functionalized the hydrochar using sulfonic nitrate and phosphate groups, and then used it for this HAA reaction, which leads to the formation of C15 fuel precursors under solvent conditions. These are biofuel precursors, and we eventually were able to get this biofuel precursors prepared using this catalyst. And this work was also highlighted by several news media during that time. And in the beginning of this year, 2023, we published one article in Fuel Journal, wherein we have taken this niobium pentoxide and grafted it with sulfonic acid group and used it for the solventless conversion of the biomass derivatives to high value carbon biofuel precursors. All these works were done by my former PhD scholar, Dr. Trapti Chavda. Now, moving on to the second part of my talk, wherein I will be talking about organic transformation reaction. Particularly, I would like to focus your attention on this hydrogen transfer reactions. Why hydrogen transfer reactions are important? Because the hydrogen source used here is easy to handle, unlike the molecular hydrogen, which is much more difficult to handle. And hence, the possible casualties could be minimized. And we are also using a mild reaction conditions, which can result in enhanced selectivity. So what we have done is we have prepared a catalyst, again the graphitic carbonitrate based catalyst by chemical oxidation method, and this leads to a lot of functionalization of this graphitic carbonitrate nanosheets. So typically the chemical oxidation leads to the hydrophilic functional groups kind of incorporated on the surface of the graphitic carbonitrate nanosheets. This includes the OH functional group, the COOH functional group, and also the carbonyl functional groups. And these act as the catalytic active sites for the hydrogen transfer reactions. And this material, we call it as the oxidized form of graphitic carbonitrate, OGCN. These nanosheets act as metal-free heterogeneous catalyst for the sustainable hydrogen transfer reactions under mild conditions. And this is how we prepared this catalyst. We started from this lysium diamide. We calcined it at 550 degrees centigrade to obtain the normal graphitic carbon nitride nanosheets. And subsequently, by having this acid treatment, wherein HNO3 along with H2SO4 was used for the functionalization, the oxidation, where an oxidizing agent H2O2 has been utilized. So that's how we end up getting this oxidized form of graphitic carbon nitride. And similar to the previous work, where whenever we prepare a catalyst, we need to do a detailed characterization of the catalyst in order to understand whether the catalyst has the structure as we have expected and what is the morphology of the catalyst. For understanding the structure and the thermal stability of the catalyst, we have done the Browder X-ray diffraction, the Raman spectroscopic technique analysis, and also the FTAR analysis, which indicates whether the material preparation is successful, what is the crystalline nature of the material, and also what are the different functional groups which are attached to this material. And from the thermogravimetric analysis, we are able to figure out what is the thermal stability of our catalyst material. Subsequently, we have done the morphological studies using SEM and the TEM. SEM stands for the scanning electron microscopic technique, and TEM stands for the transmission electron microscopic technique. And this coupled with the elemental mapping and the EDAX, which provides a lot of valuable information regarding the morphology and also the elemental distribution across the sample. Then we did a very detailed analysis of the sample using the XPS spectroscopy, which indicates how the different elements are kind of interacting with each other, and also what are the oxidation states of the different involved elements, and what is the surface composition of the elements which are present in the material. In the interest of time, I'm not going deeper into the analysis of this technique, but we are showing it to kind of inform you all that we have done all this detailed characterization of the samples in order to understand what are the underlying physicochemical properties of the sample and also the structure and the morphology of the sample. Subsequently, we have utilized this as a catalyst for the organic transformation reaction, which is the hydrogen transfer reaction, wherein we reacted 4-chlorobenzaldehyde with 2-propanol in the presence of our catalyst under certain conditions, which are illustrated here, to obtain 4-chlorobenzyl alcohol and also acetone. So what actually happens here is the 2-propanol is acting both as a solvent as well as a reactant, so which is a neat reaction. So which means this hydrogen and the hydrogen which is shown here, these two hydrogen are kind of combining with this CHO group here to lead to the formation of this benzyl alcohol moiety. And we have done a detailed optimization of the reaction condition. In one of the conditions, we achieved a very high yield of 92%. We also examined the wide scope of this material by doing a detailed substrate scope study, wherein we have taken different forms of the carbonyl substrates and then used our catalyst to form the corresponding products, and we got them in high yield and high turnover numbers, which are shown here. And the substrates which we have tried are not only the aromatic substrates, but we have also tried aliphatic substrate, and our reactions are going on both with the aromatic as well as with the aliphatic substrate, and both with electron withdrawing and the other type of functional groups which are involved in this material. Then we have analyzed the different green matrix parameters. And these green matrix parameters include here the environmental factor, atomic economy, mass intensity, process mass intensity, reaction mass efficiency, and the carbon economy. And we got quite good values for these parameters, which indicates that our reactions are green in nature. Because anything which we call green is how green, how much green. So it all have to be quantified using some numeric parameters, and these green matrix parameters are the ones which can quantify the greenness of this work. So that we have done a detailed calculation. And this work was published in the Green Chemistry Journal in 2020 with my former PhD scholar, Dr. Priyanka Chaudhary, as the first author. And this work also got a lot of news media attention during that period of time. And in a subsequent work, we have again used a sulfonyl functionalized graphitic carbon nitride and used it as a solid acid-based bifunctional catalyst for Navanagel condensation reaction and also multi-component tandem reaction. So this is also another very interesting work. But here we have functionalized the graphitic carbon nitride using the sulfonic acid by taking sulfuric acid strategy, whereas in the other case, we have used chlorosulfonic acid. So we can do different strategies for the material preparation, and the same type of catalyst or similar type of catalyst can be used for various different reactions. One case it was for the biomass valorization, in another case it can be used for that organic transformation. So this work was published in Material Chemistry Frontiers in 2021. In subsequent work, we have again taken graphite carbonitrate and used phosphorylation. It's a functionalization, and this catalyst has been used for the metal-free synthesis of primary amides. And this work was published in Chemical Engineering Journal in 2022. In a very recent work, which is published a couple of months ago, which is on boron nitrate. We not only worked with graphite carbonitrate, but we also work with other type of materials as well. And one such material which has caught our attention recently is this boron nitrate material. It's very difficult to functionalize this boron nitrate material because it's not so easy and amenable for the functionalization. Nevertheless, the boron nitrate can be functionalized, especially the periphery of the boron nitrate can be functionalized. And we have done this functionalization using hydroxyl groups, and we have used this as a catalyst for this ipso hydroxylation of aryl boronic acids, and this work was published in ACS Applied Materials and Interfaces in the beginning of this year. And very recently, just I think about some weeks ago, we have published one article in the Chemical Engineering Journal. This is again on boron nitrate, wherein we have sulfonated the boron nitrate and used it for the catalytic synthesis of aromatic nitriles under very mild conditions. All these works have been done by my former PhD scholar, Dr. Priyanka Chaudhary. Now, moving on to the next part of the talk, which is on carbon dioxide conversion. So, we have used the boron doped graphite carbon nitride again for the carbon dioxide conversion. Carbon dioxide, as we all know, this is a greenhouse gas, and there is a lot of hue and cry regarding the carbon dioxide. But, however, from a chemist perspective, carbon dioxide is a very good precursor for producing several value added products. All that we need to know is how to kind of convert this carbon dioxide into a more valuable product. So for this, we have kind of used the catalyst for this conversion. So what we exactly we have done is we have kind of taken this epoxides and we have made the epoxide to react with the carbon dioxide to produce cyclic carbonates. And as we all know, cyclic carbonates are again another type of a platform chemical which has a lot of value in several industries. So although this conversion, the epoxide to cyclic carbonates through this carbon dioxide strategy is quite well known. Our unique point or the challenge which we have addressed is we have done all this conversion under atmospheric pressure and under stable condition. So this is something which is very important because by using a pressure reactor, you can still do these reactions in a very easy way. But nevertheless, getting these reactions to work at atmospheric pressure is kind of it's a big challenge, and it's also a very good energy saving strategy as well. So we have done these reactions in this way. And furthermore, we have kind of designed this catalyst accordingly so that the catalyst is kind of very apt for this particular reaction. So what we have done in this case is we have kind of designed this catalyst to have a dual functionality. Because of the boron presence in the graphite carbonitrate, it brings in the acidic nature to the catalyst, which is the Lewis acidic nature. Subsequently, the nitrogens which are present in this graphite carbonitrate that bring in the basic nature to the catalyst. So the catalyst, the same catalyst is having a acidic nature as well as a basic nature. And the acidic nature of the catalyst activates the epoxide ring by opening this epoxide ring. This is that epoxide ring. This gets opened up due to the presence of the acidic sites which are in the catalyst. Subsequently, the carbon dioxide, which is an acid molecule by itself, it kind of adheres or absorbs onto the basic sites which are present in the catalyst, and that leads to the promotion of this carbon dioxide to form the cyclic carbonates. And this is how we prepared this catalyst. And we not prepared the catalyst in varying percentages of boron ranging from 1 weight percent to 15 weight percent. And we have done a detailed analysis of the catalyst using powder X-ray diffraction, FTIR spectroscopy, Raman spectroscopy, and also the thermogravimetric analysis to study whether the catalyst is formed according to our expectations and what are the functional groups involved and what is the thermal stability of the catalyst. Subsequently, we also did the morphological analysis using SEM and the TEM techniques coupled with the elemental mapping and EDAX technique, which can clearly show that this catalyst is forming a sheet type of a structure, and also this is the elemental distribution on the catalyst surface. Then we did the XPS analysis to understand the oxidation state of the various elements present on the catalyst and also the internal electronic interactions between the different elements in the catalyst. Then we did a detailed optimization of this reaction, wherein we optimized the catalyst first, especially the boron amount of the catalyst, and we found that the catalyst which is having 5-8% of boron showed the optimal or the best photocatalytic, best catalytic activity. Then we did the optimization of the catalyst amount, which shows the 100 milligram is the optimal amount. We optimize the reactant amount, we optimize the temperature, we optimize the timing of the reaction. Although we can see that the timing of the reaction is increased, which is about 60 hours. But given the condition that we are not using a pressure reactor and we are doing the reactions at atmospheric kind of pressure conditions, this is quite a good achievement, I would say. And we also kind of improved the catalytic activity by adding a co-catalyst. And in our case, we used potassium iodide as the co-catalyst, and we found that adding about 20 milligrams of the potassium iodide co-catalyst further improves the yield of the reaction. Then we examined the substrate scope of this reaction by trying the trying different reactants having different substituents, some electron withdrawing property substituents, some electron donating property substituent, and some are aliphatic in nature and some are aromatic in nature. So we have tried different substituents and examined the substrate scope, and we were able to successfully demonstrate that our catalyst is kind of generic in nature, which can act with different type of epoxide based materials. Then, based on our experimental results, we have, and by looking at literature, we have proposed a mechanism, and we found why this catalyst is quite active in for this carbon dioxide conversion. And we also did the since this catalyst is heterogeneous in nature, we also did the recyclability of our heterogeneous catalyst. And after every cycle, we'll take out the catalyst, we'll wash it with water, and before using for the next cycle. So in this regard, the potassium iodide, which is soluble in water, gets lost during the process. But so that's the reason we have to kind of replenish this potassium iodide for after each cycle. But nevertheless, we were able to demonstrate that the catalytic activity is preserved despite multiple cycles. We also did a detailed postmortem analysis of the recycled catalyst or the spent catalyst, and we were able to kind of understand that the catalyst maintains its structural integrity after multiple cycles. This work was published in the Journal of CO2 Utilization in the year 2021 with my former PhD scholar, Dr. Hussein Chand, as the first author. Then, very recently, just a week or two ago, we published yet another article in Fuel. And although it got the number for 2024 because they are always ahead. So, in this work, what we have done is we have did a detailed comparison study of the graphitic carbohydrates prepared from different precursors, and when we utilize them for this carbon dioxide conversion, how the source of the graphitic carbohydrate influences the final conversion yield, which is a very interesting correlation type of a study, which we have recently published in Fuel. And this work was also done by my former PhD scholar, Hussein. Now, shifting gears, now we'll move on to some work on the photocatalysis. So, the kind of holy grail of photocatalysis is how we can best utilize the total solar spectrum. So, when we look at the solar spectrum, only 5% of the solar spectrum falls in the ultraviolet region. 43% with a much more higher intensity falls in the falls in the visible light region, and remaining 52% of the solar radiation is in the near infrared region. So there's a lot of research groups which are working on how to improve this photocatalytic activity, and mainly how we can enhance this photocatalytic activity by utilizing the total solar spectrum. Especially our group is focusing on how to utilize the kind of ignored region, which is the near infrared region, also for the photocatalytic activity purpose. So in this regard, what we have done is we have prepared some unique nanoparticles called as this upconversion nanoparticles. I should not say it unique, but it's a different type of a nanoparticle which can be regarded as a new generation fluorophore. Basically, this upconversion nanoparticles can convert the light, the near infrared light, into a visible light or into a ultraviolet light. So which is it basically absorbs a low energy light and converts it into a higher energy light with non-linear optical process. So these UCNPs are extensively utilized for biomedical applications like bioimaging and thermostic. But at the same time, this material can also be utilized for photovoltaics and photocatalysis. So that's what we have kind of explored and done. So when we look at this subconversion nanoparticle, it basically consists of sodium yttrium fluoride as a lattice. It's a nanocrystal type of a lattice, and this lattice is doped with certain lanthanide anions, lanthanide cations such as ytterbium and erbium. And this lanthanide cations, one of them act as the substrate activator, and the other one also plays an active role. And by tuning the identity of the this lanthanide material, we can tune what is the emission of the light. If we have the NAR light impinging on it, multi-photon NAR light. It can kind of, if you have ytterbium with erbium, it will emit green light. If you have ytterbium with holmium, it will emit red light. If you have ytterbium with thulium, it will emit blue light and also some light in the UV light, UV region. So basically, when we look at it, the conventional luminescence, there is an excitation to a much higher energy level, the excitation of the photons, excitation of the electrons, and then there is a non-radiative decay, and then there is a emission from a much lower level. So in these kind of conventional luminescence, the emitted light is having lesser energy than the excited light, excited photon. On the other hand, when we see the upconversion emission, it's a multi-photon process. There is absorption of one photon, there is absorption of another photon, and subsequently there is an emission which is happening from a higher energy level to the lowest energy level, which indicates that this photon has a much higher energy compared to the other two photons. So this is the difference between a conventional luminescence and an upconversion luminescence. Then what we have done is we have prepared an upconversion nanoparticle. We have taken sodium yttrium gadolinium fluoride, which can also be used in the place of sodium yttrium fluoride. We have doped it with ytterbium and thulium, and then we have kind of supported it or made it as a core shell type of a nanoparticle by having another layer of sodium yttrium gadolinium fluoride. So this is basically the upconversion nanoparticle, which can convert the near infrared light into UV light and also visible light. And on the other hand, we have taken a nitrogen doped zetano, wherein we have it's a semiconducting material, wherein we have matched the band gap of the semiconductor to kind of fall within the region of this light which is emitted from the upconversion nanoparticle. So basically, the light which is emitted from the upconversion nanoparticle gets absorbed onto this semiconductor. So when it's absorbed by the semiconductor, that will lead to the promotion of an electron from the valence band to the conduction band. And in order to enhance this photocatalytic effect, we have also decorated this material using gold nanoparticles, which is having the surface plasmon resonance effect, which can further enhance the visible light absorption capability. And similar to the previous works, we have done detailed characterization of our material using X-ray diffraction pattern. And also we have prepared this material using various weight percentage of these compounds. Then we have also investigated the UV spectra and the upconversion luminescence of this material. And the upconversion luminescence, you can clearly see that when this material is dispersed in water and taken in a cuvette, when we shine the infrared laser, you can see wherever the laser is kind of impinging on this material, you can see this blue colored line or blue colored streak, which indicates that the upconversion nanoparticles are present because it's getting converted. The NIR light, we cannot see it with our eyes. And when it passes through this material, this gets converted to the blue light, which can be seen very clearly, visibly as well. And this can also be upconversion luminescence spectra can also be recorded using the instrument. Then we did the morphological study using SEM analysis and also the TEM analysis, which indicated what type of material is being formed. So with the upconversion nanoparticles, it's a core shell type of a structure. The end-doped zetano, it's a sheet type of a structure. And finally, the gold nanoparticles, these are again small spherical type of a structure, which is kind of decorated onto this material. Then we did a detailed XPS analysis to understand more information about the different surface properties, surface electronic properties of this material. Then we did the reels and the UPS spectra in order to understand what is the band gap. Experimentally, we can determine the band gap, especially the valence band edge position. We were able to experimentally determine, and then we were able to figure out what is the band gap of this material. Then once we did all these characterizations, we have utilized this for the photocatalytic degradation of one of the well-known pharmaceutical pollutant, which is the tetracycline. And this tetracycline is a colorless pollutant. We purposely chose a colorless pollutant because we do not want the photosensitization effect to be included in this case. It should be a pure catalytic effect. That's the reason we did not use any colored dyes or anything, and we have used a uncolored or a colorless tetracycline. First, we did the experiment under the NAR light irradiation. We have a solar simulator. We blocked the visible light and the UV light using a thick bandpass filter, which lets only the NAR light to pass through with this photocatalytic degradation of this tetracycline. And we found that one of the sample, which is the AZU05, gave the best result, which shows that it's the upconversion nanoparticle which is the main player of the reaction. Whereas the gold and Zetano, they have a less role, which we will be seeing it. They don't have a direct role, but obviously they have an indirect role, which we will examine it in the mechanism part. So nevertheless, the upconversion nanoparticle is able to do this photocatalytic conversion. That's what is the bottom line. Then we did the same reaction under visible light radiation, and here it's the gold nanoparticle and its SPR effect, which is kind of playing the major role. And we could clearly see that the AZ is exhibiting the best photocatalytic activity among all these samples. Then we also did the same reaction under UV light irradiation, which indicated the NZNO playing the major role and showing the best photocatalytic activity, which is also expected because this is a UV active material and it should show good photocatalytic activity. And finally, we kind of deciphered this mechanism of the reaction. So especially when this NAR light is falling onto this upconversion nanoparticle, so we have this core shell type of the upconversion nanoparticle, and due to the nonlinear optical processes which are involved in this upconversion thing, it emits the visible light and also the UV light. The emitted UV light is kind of absorbed by this end-doped ZNO, which is shown here in this wavy type of a structure. This is absorbed, and that leads to the promotion of an electron from the valence band to the conduction band, and that leads to the degradation of this pollutant tetracycline. On the other hand, the visible light, which is again emitted by the upconversion nanoparticle, that kind of impinges onto this gold nanoparticle, and due to the SPR effect, that leads to the promotion of an electron from the gold nanoparticle to the conduction band of this semiconductor, and again those electrons lead to the degradation of the pollutant. And this work was published in the beginning of this year in separation and purification technology with my former PhD scholar Dr. Ajay Kumar as the first author. And subsequently, we have also worked on Maxine-based material. We have coupled this Maxine with graphite carbon nitrate and used it as a plasmonic photocatalyst for the removal of pharmaceutical pollutants, obviously after decorating them with the gold nanoparticles. And then at another work, we have again yeah, taken the gold decorated graphite carbon nitrate nanocomposites and used it yeah, for controlling the kinetics of the visible light induced photocatalytic activity, wherein we coupled them with different proteins, and some of the proteins enhance the kinetics and some of them decelerate the process. For example, we have used bovenserum, albumin, trypsin, and cytochrome C, three different proteins. When we use BSA, the kinetics is made faster, whereas on the other hand, if you use trypsin and cytochrome C, the kinetics are slower. We have also analyzed why it is so happening so, and we have given a detailed write-up about them in this publication, which was in Journal of Environmental Chemical Engineering. And we have also written two review articles on plasmonic photocatalysis. One on the graphitic carbon nitrate based plasmonic photocatalysis, which was published in the Material Chemistry for Frontiers in 2023, in the beginning of this year. And another review article in 2022, which was published in Small, wherein we have discussed the plasmonic photocatalysis of TiO2 based materials. Then now moving on to the final part of my talk, which is on nitrogen fixation. So nitrogen fixation, it's a very important topic wherein nitrogen fixation is the one wherein nitrogen gets converted to ammonia. So till date, ammonia is being produced only by using the Haber-Bosch process, which is energy intensive process, and also the catalyst which are used are more expensive, and it is not a sustainable process. On the other hand, if we can kind of find a sustainable way to make the conversion of nitrogen to ammonia feasible, that would really be open up a lot of doors. So because nitrogen is a gas which is abundant in the atmosphere. On the other hand, it requires hydrogen. Hydrogen can also be obtained from water by doing water splitting. So the water is again another abundant resource which is found on the earth. Then if we can combine these two abundant resources in the presence of another abundant resource, which is the sunlight, in the presence of our catalyst, it can do really wonders. So that's what we have tried to do in this work. And typically, if we want to do this one, we have to have maximum harvesting of the sunlight. So there is a huge light harvesting which is required. So the best way to look at it is we can take inspiration from a plant leaf, because plant leaves can harvest the light in so many different ways, and because of the micro and nanostructures which are present on their surface, and we can take a lot of inspiration from them. So that's what we have done in this book. We have taken a plant leaf, it's the sacred fig leaf, Ficus religiosa, but you can take any plant leaf and then do some sort of a treatment and finally prepare a leaf inspired calcium titanate material. So this this is a material which has this micro and nanostructures of the leaf embedded on this material. Then we can kind of introduce certain defects onto this material. The defects are pretty much the oxygen vacancy defects, and these defects kind of have the high charge localization, which are selectively distributed across the catalyst. And these defects, or the oxygen vacancy defects, make the nitrogen to get absorbed onto them. And because of this high energy which are present, or due to the high charges, these bonds can get broken. Then if you can, the problem with the nitrogen is it has this triple bond, and it requires a very high energy to break this nitrogen into multiple things. So if we can successfully do that, that would really do a lot of wonders. And if you can see it here, so this is the SCM image, wherein you can of the secretary leaf. You can see the beautiful micro and nanostructures which are over there. On the other hand, if this is the calcium titanate, the leaf-inspired calcium titanate, which is also having a lot of micro and nanostructures which are there, which are kind of exact replica of these micro and nanostructures. All the carbonaceous material of the leaf is gone in this case. However, it is only the micro and nanostructures of the leaf which are being prepared. Basically, we have used leaf as a template to create those, replicate those micro and nanostructures onto this material. If we do not use the leaf as a template, we will simply end up with some powder based material. Then we have done a detailed characterization of this material using powder X-ray diffraction, Raman spectroscopy, the EPR, and also the XPS. And the EPR and XPS will give a clear understanding of what type of oxygen vacancies which are present in this material, and how they are kind of influencing the structure and properties of this material. From the XPS, we are able to see the titanium, with normally in calcium titanate exhibits +4 oxidation state, but because of the oxygen vacancies, we are able to see not only the +4 oxidation state of titanium, but also the +3 oxidation state of titanium. This is a clear indication of the presence of a oxygen vacancy. On the other hand, the EPR is also showing certain signals which indicates the formation of the vacancies. And we have done a detailed XPS analysis, and also a detailed HRTEM analysis, which also indicates the presence of the oxygen vacancies. We are able to identify the presence of the oxygen vacancies, but however, it's not easily possible to quantify the oxygen vacancies. But nevertheless, the identification is quite a good enough way. Then we utilize this catalyst first for the hydrogen evolution, because the same catalyst can be used for both the hydrogen evolution and also the nitrogen fixation. And the hydrogen, which and every experiment here is being done under the direct sunlight irradiation. So the hydrogen which is evolved from water was made to combine with the nitrogen, and finally we were able to get the ammonia. And we are also examining the recyclability of this reaction. We also did a detailed theoretical analysis of the reaction using density functional theory, in collaboration with the group of Dr. Saswata Bhattacharya from IIT Delhi. And we kind of came up with the possible mechanisms first for the hydrogen evolution, because the same catalyst is effective for both hydrogen evolution and nitrogen fixation. So we did the hydrogen evolution and plausible mechanism, and the nitrogen fixation possible mechanism. We were able to figure out that the photocatalytic hydrogen which is evolved is about 3418 micromole per hour per gram, with the STH. STH is the solar to hydrogen conversion efficiency of 1.17, which is not a great value, but nevertheless it is kind of it kind of matches with the current state of the art values. And then we utilize the same catalyst for the nitrogen fixation, which is the nitrogen to ammonia conversion, which leads to a value of about 236.12 micromole per hour per gram, which is 4 times higher than the pristine calcium titanate. And this work was done by my former PhD scholar, Dr. Ashish Kumar, and was published in Journal of Material Chemistry A in 2021. This work also grabbed a lot of news media attention during that time. And as a follow-up work, we have worked on strontium titanate. And the strontium titanate, we have utilized again by introducing certain defects for this photocatalytic nitrogen fixation. And here we have done all this reaction in pure water. And this work was also done by Ashish Kumar, and it was published in Nanoscale in sometime in the middle of this year. Then we have written 2 review articles. One review article on perovskite oxide-based materials for energy and environment-oriented photocatalysis, which was published in ACS Catalysis. This review article was written during the first lockdown period, the COVID lockdown period here in India. And this work also got featured on the front cover of this ACS Catalysis journal. And then we have written another review article on vacancy engineering in semiconductor photocatalysis, mainly about its implications on hydrogen evolution and nitrogen fixation. This was published in Advanced Functional Materials in 2021. So overall, I would like to state that our group is actively working in the domain of heterogeneous catalysis for energy and environment application. And today I gave a brief kind of overview about the activities which are going on in our group, the domain of biomass conversion, organic transformation, carbon dioxide reduction, and also about pollutant degradation and the nitrogen fixation and hydrogen evolution in a combined way. And finally, I would like to once again thank all the members of my research group and the faculty colleagues and staffs here at IIT Mandi for their kind support, research collaborators both within and outside IIT Mandi, and also the our centralized instrumentation facility, which is the Advanced Material Research Center for all the instrumentation and the facility support. And these are the different funding agencies that have funded our research work. And finally, a bit of advertisement. I have recently joined this new Journal of Chemistry, which is an RSC journal as an associate editor. So please do submit some of your good works to this journal. And I'm also on the editorial advisory board of this ACS ESNT Engineering, which is an ACS journal. So please also consider submitting some of your works to in this journal as well. And finally, I would like to thank you all. And I really appreciate the opportunity given by Dr. Dinesh Pathak for sharing our research group interest with you all. Thank you. Thank you very much.
Thank you,
Over to you,
Professor
Dinesh.
Venkata, for showering the latest knowledge on nanomaterials for energy and other applications. I hope that we will try to have some cooperation, academic cooperation with your group soon. And
Yeah, that would be great.
yeah, we because we run here BSc, which has minor in material science, so we have some students in that case, and we have UG projects also, and then especially
Mhm.
we have MSc, which is biomedical technology, and MSc, which is renewable energy, where we have courses like hydrogen energy, energy storage, and biomedical materials, especially for the bone implants or maybe the dental implants, etc. So many things like that. So we will discuss that in detail
Sure.
soon. And you are also welcome to visit here at the University of the West Indies, which is
Great. Yeah. Thanks a lot for the invitation. Sure.
yeah,
I
yeah,
will
yeah.
definitely consider sometime. Yeah.
So you may have some change also as you are daily looking the Himalaya and Dholadhar. So you can see
Yeah.
in all sides here
Oh,
at
fantastic.
every side
Good,
because
good, good.
all countries are without landlock. Everywhere we have
Okay.
sea, Caribbean
Hmm.
Sea or the North Atlantic, whatever. So that
Great.
you are welcome to visit means that is what I was saying.
Sure, sure,
That
sure.
soon
Thank
we
you.
could
Thank you.
plan such initiatives, and
Great.
I must say thank to you on behalf of head of the department because he has some other engagement, so he could not join. He was there, but he went somewhere for the interviews. And
Okay.
now
Okay.
we, before finally going to the that vote of thank by Dr. Binod Kumar, who work here, a faculty member in renewable energy and technology. So we can have
Yeah.
some questions if we wish to
Sure, sure, sure. I'm
discuss
open
something.
for any questions.
And even I said that Professor Venkata is very active in research, and he's one of the other thing is that he is very polite person. Whenever you mail him, he will definitely reply you, and you can get information from him either in research or maybe in academic advising. So
Sure.
we can have some questions, and particularly, Dr. Benta, I just want to, if you can comment on the negative side of nanomaterials, because everywhere
Mm-hmm.
we are forcing nanomaterial in catalysis or
Mm-hmm.
maybe energy in batteries everywhere. So we are miniaturizing the size to very small scale.
Mm-hmm.
Uh, some special nanostructure, maybe the different size shape structure, and so
Mm-hmm.
sometimes we people are also worried about the negative side of nanomaterials. So if you can just enlighten some of the participant here who are live or maybe later who will see the recording that
Mm-hmm.
your comment, because you belong to chemistry and you have better opinion on that. So if you can just comment on the negative side of nanotechnology, if the materials can be harmful, how much, what are the policies for this, especially in this direction. So I'm not much aware. I belong to physics, but you are a chemical person, so you can, if you can comment. This is just only the
Sure, so that's a very
request from my
interesting
side.
and very important question.
Yeah, thank
Exactly.
you.
But the nanomaterials, these are kind of really soaring heights, and a lot of research work and also experimental application. It's just on the search. There is a lot of positive impact which this nanomaterials are creating in science as well, science and technology, and also in industries. At the same time, there may be some several associated negative implications as well. So many cases, the kind of intrinsic toxicity of these nanomaterials are not fully evaluated. For example, the Nobel Prize for this year in chemistry is given for the quantum dots, which the people have showed that how the size of the quantum dot determines the color of their appearance. So the same gold quantum dot is showing different colors when depending on its size. At the same time, if the color is changing, which is an optical property, obviously the toxicity of the nanomaterial may also change. For example, whatever we consider it as small, it may have a different impact. For example, just to give a simple things, if individually things may be having a different toxicity, but put together they may have a lower toxicity or can have a higher toxicity. For example, the sodium chloride. Sodium, as we know, it's highly reactive. If it just sees water, it can explode. Sodium's reactivity is quite well known. On the other hand, chlorine, when we see, it's also a kind of so-called toxic gas or a poisonous gas. It's not quite good to inhale or something. But when these two kind of combine to form sodium chloride is a simple salt. It's very stable. We eat it almost every other day. Although individually, when we see, look at the elemental level, the sodium and chlorine, this could be kind of toxic if they are separate. At the same time, in a similar way as an analogy, if we take the nanomaterial, if we may take see that, oh, gold is completely inert. Gold is quite safe. Even they make it them gold basma or something for consumption as well. I don't consume, but nevertheless, in some cases, it is still kind of considered to be safe for consumption, etc. Although depending on the cost, I don't think anyone consumes gold. But nevertheless, the gold or any other type of a nanomaterials, if the size kind of reduces, it may have a lot of pathological impact. So that assessment has not been completely done, and it is also not so easy to do it because different categories of nanomaterials, depending on the size, shape, and properties, it will have different impact. The same, the nanospheres may not be that dangerous, but at the same time, nanoneedles or nanorods or nanotubes may have certain health-related implications. There are some works which are being done, but lot more to be are yet to be done. So these are some of the negative things, especially with regard to the toxicity and the pathological nature of these nanomaterials. Beyond that, I do not see any other direct negative things about the nanomaterial. I'm not sure. Yeah. But
Okay,
that's
thank
toxicity
you,
is the negative.
thank you once again. So
Thank
I
you.
hope that this comment will be helpful for our students studying the biomedical technology, etc. So, Dr. Binod, do you have some question?
Yes, I have one question.
Yeah.
Thank you very much, Professor Krishna, for a nice talk on energy and environment. It's very
Thank
informative,
you.
informative talk. Uh, I have some query or some information I want related to the up conversion part. You provide very nice information how we can convert the NIR to the visual part.
Yes.
And I am. Can you explain how much easy to control this up conversion as it is a non-linear process? So, what is the
Yes.
quantum
Yes.
yield? Because I see many people they explain, but
Mm.
sometimes the quantum yield is not control. This is the first
Mm.
part, and the second part is very interested up conversion with plasmonic. So, can you explore a little bit
Mm.
how you decorate the plasmonic and what is the benefit of plasmonic and up conversion together? Can you explain a little bit, please?
Exactly. Sure, sure, sure. Definitely. It will be my pleasure to explain this one. So, first one regarding the quantum yield. Quantum yield is a very important parameter, and we need some certain dedicated, separate facilities and the infrastructure and the instruments to kind of measure the quantum yield. Unfortunately, at our institute, we do not have the that required capabilities or the instrumentation facilities to measure the quantum yield. So we have not done the measurement of the quantum yield in for any of our conversion nanoparticles. That is one thing. Although there's a lot of work which is being done on measuring the quantum yield, but just that we do not have the facility, we didn't measure. And the secondly, our work doesn't require the measurement of the quantum yield, because all that we wanted to do is we wanted to show that a upconversion nanoparticle can also be utilized for the photocatalytic applications. And this is the one of the strategy by integrating the upconversion nanoparticles with a plasmonic material and also a semiconducting material, and utilizing them for the photocatalytic application. So this is this was our kind of objective. In this way, we kind of took our storyline. So although if we would have taken it in the quantum field, then we could have done a lot more theoretical or physical studies, and that could have gone in a different direction. But we don't have the capabilities. We didn't do that. But we for our research work, it was not to tell our story. That was not so important. That's the reason we didn't explore the quantum field in too much in depth. And secondly, to kind of decorate the gold nanoparticles on the upconversion nanoparticles, we have utilized a well-known strategy, the synthesis strategy, and we kind of coupled them. Let me again share my screen and I'll show you the synthesis strategy, wherein you can clearly see how this has been done. Is my screen visible?
Yes.
Is my screen visible?
Yes.
Yeah.
Yes, Professor.
Good, good, good. I'm just going back to the concerned slide. So this is how we did it. So we kind of prepared this upconversion nanoparticle separately. Then we prepared the end-doped ZNO separately. Then we have kind of combined these two together. Then we have prepared the gold nanoparticle in appropriate size. Typically, the gold nanoparticles are around 17 nanometers. We use a seed-based technique for the preparation of the gold nanoparticle, 8 nanometer seed, and then subsequently it's grown to about 17 nanometers. Then we kind of mixed that, and gold nanoparticle, the concentration is only 2 weight%, because we do not need a lot of gold nanoparticles. We just need 2 weight%. We just kind of mixed them all and then stirred them for about 3 hours to ensure that they are all very, very well mixed. And then we transferred onto the hydrothermal reactor, which is this Teflon lined autoclave. And then we kind of heated it in an oven for about 120 degrees C for a 10-hour duration, to end up like this AZU type of a composite. So this is how we prepared this upconversion nanocomposite upconversion material combined with this NZNO nanosheets and along decorated by gold nanoparticles. So this is a ternary type of a material which we prepared using a simple mixing type of a technique. The catch is the stirring time kind of determines how well all these materials are distributed, and we are taking these materials in appropriate weight percentages. So that's how we prepared this material. And and also yeah, we did different analysis in order to understand how they are distributed. We did the TEM and the SEM analysis to figure out whether they are all kind of quite well distributed across, or they are all for kind of localized and making clusters or not. That also we studied it using the different morphological techniques. So that's my answer to the second question. I do not know whether my answers are have satisfied you or not, but this is my answer.
No, no. Thank you very much, Professor.
Yeah,
It's actually why I was interested. People are working the upconversion separately and plasmonic separately, but this is very interested
yes,
work.
yes, yes.
Both approach you work and you merge both approach together. So I think this
Mhm.
go in the new direction and better results. Thank you very much,
Yeah, yeah, yeah. It's my
Dr.
pleasure.
Pathak.
Okay, okay. So if we have some question from the student side, uh, I saw some students there from the ceramic science. Miss Nirmala or maybe someone else if you have some question. Okay. So if not, then for the addressing the people, those who are not here, although we have much strength, but sometimes people don't appear on the live that lectures. But if you see later, you can contact Professor Venkata for discussion, academic advising,
Sure.
how to go for PhD in Germany later maybe, and something whatever you feel, how to participate in Lindau Novel Laureate meeting. He was also one of the participants, and yeah, so you can just talk with him. You can search his group BKN group on the Google IIT Mandi, and we will make some academic cooperation later, and we will be happy to invite him here at Port of Spain, which is the capital of Trinidad and Tobago. Okay, okay.
Great.
So
Sure,
I
sure.
request, yeah, thank you. I request Dr. Binod to say both of thank from on the behalf of Department of Physics, Faculty of Science and Technology, the University of the West Indies, before we close the session. Thank you.
I see a question, sir. You can come for T20. I do not know what is T20. If I get an invite and if my dates are available, I'll be
Yeah,
more than happy
T20
to.
because see, Dr. Venkata, this is Caribbean and the West Indies is famous for the cricket. So this is T20 is the 2020 cricket tournament. Maybe you can meet with
Oh,
Brian
okay.
Lara.
Yeah, yeah,
See,
yeah, yeah.
everybody.
Now I
Yeah,
get
yeah,
it.
yeah.
Because
So
we are
she's
thinking science. We thought G20. Now, a lot of activities are going
yeah,
on in
yeah,
India
yeah, yeah.
regarding the
So
G20 because India is the
yeah,
president of
see,
this G20.
because
So I
with
thought
the
G20 and S20, T20. Now
yeah,
almost
yeah,
all
yeah. So
alphabets with 20.
So the thing is that
Yeah.
these all countries they play cricket together, although the countries are separate
Mm,
with the different governments. But when they
mm,
play cricket, they join the hand together, and the team becomes the West Indies team. So here we
mm,
have
mm.
the cricket culture too much, maybe gifted by the British
Okay.
people who have were here for a long time.
Yeah.
And so we
Okay.
have the cricket stadium everywhere here, like Brian Lara Academy and many
Mm.
others. So this student, Miss Nirmala Singh, she study material science in UG. And so
Oh, good,
she
good.
may be inviting you for T20 cricket
Oh,
tournament.
okay.
Yeah,
Yeah, yeah.
yeah.
I don't
Yeah.
follow cricket that much, so
Yeah, yeah, me
I'm
too.
not so good
Me
at
too.
it.
But here we go sometime to just to show the spirit of the country and something like
Great,
that.
exactly. I
Yeah,
understand.
yeah.
Great,
Thank you.
great,
So you're
great.
welcome to visit sometime. You can plan.
Yeah.
Visa is also not required without visa. Indians can stay here up to 3 months. Yeah,
Wow. Oh,
yeah,
that's really good to know. That's an
yeah, yeah. Yeah, thank you.
important information.
Yeah, yeah, yeah.
Yes.
Dr. Binod, maybe you can proceed for the vote of thank, and then we will close the session.
Okay, on the behalf of Department of Physics, I want to thanks very much to Professor Krishna for a nice talk on nanomaterial for energy and environment application. Your talk is very informative and especially related to heterogeneous catalysis, up-conversion nanoparticles, and nitrogen fixation. That is very important and informative for our students here. And your talk is very helpful for our student. As Dr. Pathak told, we have UG student with minor in material science and environmental science, as well as we have master, especially in renewable energy. We have master in renewable energy. So it's very helpful for them how they can go on that direction. And we can explore how we can do the long-term collaboration and academic collaboration, because we need sometime our student need some experimental help or some kind of discussion and other kind of help. So I think we can make a collaboration. Dr. Pathak can help us in this direction, how we can go for a long-term academic collaboration, and if there is some chances of like MOU and other things which can helpful for us. And other than this, we need like we need sometime the examiner, especially for our master thesis and PhD thesis, that we can explore. And of course, you are always welcome to
Sure.
visit us when you have time in your
Thank
future.
you.
And if you are coming in the USA, we are very close to from USA. It's only 3 and 4 hours from USA. From New York is 4 hours, and from Miami is 3 hours. So you are very welcome
Okay,
to
good
visit
to
our
know. Yeah.
institute, and how we can explore and how we can go in that direction. And thank you very much again for a nice talk on
It's my
today
pleasure.
occasion. And we will get
Thank you.
your guidance in that direction in future also. Thank you very much, Professor Krishna.
Thank you.
Thank you once again, Professor Venkata, and we will meet soon for all these issues.
Thank
Whatever.
you. Thank you.
Thank you. Thank you for having
Thank
your
you.
time. Yeah. Thank you.
Yeah, thank you. I'll just log off right now. Yeah, thank you. Nice
Thank you once again.
meeting you all. Thank you. Have a nice day. Yeah, goodbye. Good night.
Bye, Professor. Bye.
Yeah, for you it's a good day. For me it's a good night.